Okay, so this is number 45 from chapter 7. And really the key reason we're going over this, aside from the fact that you all asked me, made me happy. But this is a skill that you have to know how to do. Okay, you're going to do it over and over and over again. So let's make sure we got this down. Ask us some good questions if we need to. So the points, the question was, how big does the graph need to be? The points have coordinates 2, 4, oh no, wait, this isn't 45. Which one were we gonna do? We're gonna do 48. My bad. Not 45, 48. The coordinates of the points were 2, 9, 4, 3, and 9, 6. So I didn't bother doing any negatives because everything's positive. So I'm going to graph these 3 points. So they say to graph points A, which is at 2, 9. So over 2 up 9, 2, 5, 6, 7, 8, 9. Here's my A point. And then B is at 4, 3. 1, 2, 3, 4 up 3. And C is at 9, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. And I'm just going to move this down here. And what they have asked us to determine is what's closer to point A, or I'm sorry, what's closer to point B? Is A closer to B? Or is C closer to B? So in order to do this, in order to know for sure, we would need to find those two distances. C was 9, 6. Thank you. And A was 2, 9. All right, there is a thing called the distance formula, but there's another way to find distance also. If you're a formula collector, though, no, there is a thing called the distance formula. I'm going to show you a different way. And this relies on making triangles. So I'm going to find this distance here first. And I'm going to do that by creating a right triangle. I'm going to use the grid lines to create a right triangle out of that distance. That's a great question. Did you guys hear that? Could we use slope to find the distance? Slope measures how tilted a line is, kind of the angle of it. It doesn't measure distance though. However, we are going to be using slope a lot in conjunction with distance later on in this unit when we're analyzing quadrilaterals. So I'm glad that you're thinking about that right now. And there's a slope formula too. So yeah, but we can't use slope to find distance because if I took a little portion of this line, it would have the same slope as the big portion of the line, right? Yeah. We would use Pythagorean theorem. Yep, that's the key to this. So we're going to call this X because I don't know what it is. But I do know that this is 3 because I can count 1, 2, 3, and 1, 2, 3, 4, 5 down here. So we got 3, we got 5, we got X. We can set up an equation with Pythagorean theorem. 3 squared plus 5 squared equals X squared. And we have practiced Pythagorean theorem so many times this year. If you've been doing your homework, do you need some paper, Alyssa? You've got some? Okay, should get it out. 3 squared is 9, 5 squared is 25, 9 and 25 is, what is that, 34? 34 equals X squared. And then to solve this, we take a square root on both sides. I don't know what the square root of 34 is, but my calculator does. 5.8-ish, sounds right. We'll call that good. Right? Because it's a little bit smaller than 36. And the square root of 36 is 6. Good. Good for you. All right. Now that you've seen me do that, I want you to do one. Could you go ahead and create yourself a right triangle out of points A and B? And write in the distances here and here and set me up a Pythagorean equation to solve for. Let's call this one y. Go ahead and do that on your own, please. I want everybody doing it. Already slowed? Okay, thank you. All right, let me catch up to you. That's 2, 2, 3, 6, 4, and 36 is 40. 6 point, what do you think? 3, 6.3, 6.4? Do you think 6.3? It's definitely between 6 and 7, right? Because the square root of 36 is 6 and the square root of 49 is 7. This is closer to 36 than it is to 49. I think 6.3. Did anybody actually put it in their calculator? The square root of 40? 6.3? Hey, nice. I like that you're trying square roots with mental math. All right, we should be getting 6.3. All right, ask a question if you got it. If this is totally bewildering to you, that's okay. We can get you caught up. Just get my attention when we have some work time later on today. All right, let's have a look at 56. Oh, there we go. No, this is an early slip. Wow. You get to come late and leave early. Thank you for that. Just let me know when you're taking off. Okay. Let's look at 56. 56 is, it's kind of weird the way that they framed this question, but it's a cool one. And I'm going to show you, and then I'm going to show you how this helps you become a better pool player. Anybody here play billiards? Well, you got a pool table at home? Pretty good at it? Do you know all the tricks? He's good. All right, well, I'm going to teach you a math trick that's going to make you an even better pool player. But let's start by doing the actual problem here. So we got an art museum, we got a library, and then there's a road over here. Thank you very much. There's a road over here, and they told us that the art museum is 50 feet off of the road and the library is 60 feet off of the road. And the distance between these two things is 80 feet. They're pretty close together. Maybe they're very small buildings. And the idea is that who's in this problem? This is Sandra. Sandra wants to park someplace on the road here, and Sandra's going to walk into the art museum and in the library, and she just wants to make it as short a walk as possible. So she's going to park somewhere here. She's going to have to walk diagonally to both of these things, and she wants it to be as short a walk as possible. So the question is, how far along the road, I'm going to call this X right here, how far along the road does she need to park so that her walk from her car to the art museum and to the library are both as short as they possibly can be? That sounds like a pretty tough question, but there's a trick to it. And this trick also applies to billiards. I'll show you the trick. So that's what I thought at first too, was divide by 2. And if they were both the same distance away from the road, that would be correct. I think we want it to be a little bit closer to the art museum because it's closer to the road though. We'll find out in a second here. I'm going to redraw this picture here, and I'd like you to do the same because this is so cool. You guys are your mind is gonna be blown. Just wait for this. It's gonna be amazing. All right, so, I like that guess. Not actually gonna do a parallelogram, but I like that you're guessing that. All right, you ready for this? The shortest distance between 2 points is a straight line, right? You've heard that before? All right, now here's the magic. I don't know who figured this out, but I could take this library and I could reflect it across to the road. This is the tricky part. I'm going to reflect it across the road so that it's the same distance away over here. And then I'm going to draw a line straight from the art museum to the library. Not the actual library, but the pretend one that's been reflected over. Now, would you agree that this distance, this fake distance over here, would be exactly the same as this distance right here? It would have to be, right? Because this is just a reflection. Reflections preserve distance. So what we've got now, we've got this cool situation where we actually have a triangle, and we know that this is 80. And we know that this is, since we reflected this over, this would be 60 here, which would also be 60 up here. And we're trying to solve for this. So what we're going to end up using is similar triangles. We're going to set up a proportion and solve. This is like going back to chapter similarity with chapter 3. So see this little triangle right here? I'm going to sketch that. It's got a 50 and an X in it. And then this whole big triangle over here that includes that smaller one, that would be similar. And this is 80. And how long is this all the way across the top of this thing? 110, 50 plus 60 is 110. And now I can go ahead and set up a proportion to solve this thing. X matches up with 80, 50 matches up with 110. And we've solved so many of those, I'm not gonna rob you of the opportunity to practice that again. Right. Pretty neat, huh? So there's this idea of, rather than thinking of like going to the road, bouncing off and coming back, we think about going to the road and then going through it to a reflected version of the library. And this is the trick I want to show you to make you an even better pool player. Are you ready for this? This is a really good one. Okay. Don't ever ask me where would you ever use geometry in the real world, because this is it right here. Obviously, this is not the only one. You all know what a pool table looks like, right? It's a rectangle. And they are kind of curved edges, but I'm going to just draw it as a rectangle. Pool table has 6 pockets, so they're kind of holes that you try and knock the balls into. There's one at each corner, and then there's a side pocket on each side of the rectangle. Okay. One of the more difficult shots in pool is a bank shot. Okay, so in a bank shot, you've got a ball, and let's say my ball's right, say it's like right here. And I want to put that ball into this pocket right here. Okay, but let's say there's something in the way. There's another ball right here, so I can't just hit it straight into the pocket. So how am I going to do it? I'm going to have to hit the ball into this bumper right here, bounce it off, and make it come back. And it's really difficult to do because you got to hit that bumper just right in the perfect spot to get it to come back and go into that hole. Do you know the trick to this? Have you ever heard this before? So what you do, so I know that I'm going to have to hit the ball kind of towards this bumper. I know it's going to go something like this, and then it's going to bounce back to it, right? The trick to this is you imagine a reflected pool table sitting immediately next to the one that you're on. Okay. And this bumper would reflect over to this spot right here. Agreed? So you're sitting there at the actual pool table. This is all happening in your brain. You have to imagine there's another pool table sitting immediately next to it. And you have to kind of position so that the fake hole over here is the same distance away as the real hole over here. And then you aim your purple ball straight at that fake hole right there. And what's going to happen is that it's not actually going to travel through this. It's going to bounce off and it will perfectly go back into that. Yeah. Oh, was it? Donald Duck and Math Magic Land? I haven't seen that in forever, but they show this in there. Oh, cool. It does. Yeah, try it next time you're playing. So you got to get really good at like imagining just the right position of it. But once you kind of nail down where that position is, when you go to line up your shot, you're just aiming that ball straight towards that position, and it'll hit that bumper and it'll come right back to it because of reflections. All right, so remember me when you're out there on the professional pool circuit making your millions of dollars. You stand up there with your trophy, say, I want to dedicate this to my geometry teacher, Mr. Height. All right. Any other questions from homework? Are you guys ready to get after this today? We're going to do some real deal proofs today. Do y'all have books? If you don't, go ahead and grab one. You just need one for each table. Page 423 is where we're going to be working today. I need you to have your notes out.